All right, so today we are going to be moving on with parametric equations, still section 10.6 in your book, but we're going to be parameterizing parabolas and using the parametric equations to solve application problems. All right, so convert the following sets of parametric equations into rectangular equations. So right now we have a set of parametric equations which look like that. X equals a times t to the second power plus h, and y equals t plus k. So the easiest thing to do, and it doesn't matter what type of parametric equation it is the first method that we did last lesson with lines, is to solve for t. The easiest way to eliminate t is to solve for t and substitute it in. So let's take y equals t plus k, solve for t. All right, so we get t equals y minus k. So we take that now and we substitute it into the other equation for t. So we get x equals a times the quantity y minus k squared plus h. And now let's put this into a parabola. We know from the start right here that this is a parabola because only y is squared, and that's when we have a parabola. So we're going to want to solve this for the quantity being squared. So we subtract h, divide by a, and we get the parametric equation y minus k squared equals 1 over a times x minus h. So looking at this, that means that my vertex are the coordinates hk. So looking at your equation, we have the number that comes with x, the constant with x is our x coordinate of our vertex. The constant with y is our y coordinate of our vertex. And then we also have that 1 over a is equal to 4p. So that means that the reciprocal of a is equal to our 4p value. So when we are graphing a parabola, or if we're coming up with the equation, we can use either one of these methods. I personally will always solve for t, substitute in, put it in conic form, because that method works all of the time, whether it's linear, whether it's parabola, whether it's an ellipse, a hyperbola, a circle, you can always use that method. So that is my typical go-to method, is a substitution. But the only parametric equations that you're going to be tested on are going to be lines, like we did in last lesson, and parabolas, like we're doing in this lesson. So if it's easier for you just to memorize this pattern, that h and k are your vertex, and the coefficient of t squared is the reciprocal of 4p, and then convert it just like that, going straight from here to there, you absolutely can. So we'll do some examples in a minute here where we do it both ways. So number 2, let's go ahead and let's do the substitution. So I want to solve for t. So I subtract h on both sides. So I get t equals x minus h. Substitute that into my other equation. So I get y equals a times the quantity x minus h squared plus k. And now I'm going to solve for the quantity x minus h squared. So subtract k, divide by a, and we get the parabola in conic form. The quantity x minus h squared equals 1 over a times the quantity y minus k. So again, we get our vertex is hk. H comes with the x, the constant of our x equation. The k comes from the constant from our y equation. And we get 4p is the reciprocal of a. All right, so now let's put that all together. So now we're given a set of parametric equations. We want to sketch the curve represented by the parametric equations without a calculator, and use a graphing calculator to confirm your results in parametric mode. and then eliminate the parameter and write the corresponding rectangular equation. So I personally think it's easier to do C before we do anything else. So again, there are two ways that we can go about doing C. So the first way that we can go about doing C is exactly like we did up above. Take our variable that has t, or our equation that has t, solve for t. So we take x equals t plus 5 and solve for t, so we get t equals x minus 5. Then we take that and we substitute it into our other equation. Hang on, give me 1 second. Okay, sorry, I forgot where I'd put the where I'd put the equation. So we take x minus 5 substituted into the other equation for t. So that ends up giving us y equals -1/8 times the quantity x minus 5 squared plus t. And now we solve for x minus 5 squared. So we get x minus 5 squared equals -8 times the quantity y minus 3. So we go ahead and we graph that. We have our vertex at 5, 3. And our p-value, or so this is going to, since x is squared, this is going to open up or down. Since our p-value is negative, it's going to open down. So we have a parabola opening down, and our p-value is going to be equal to 2, since -8 is equal to 4p. So we have our vertex, which is at 5, 3, and then our directrix is going to be 2 units above us, and our focus is going to be 2 units below. Again, because -8 is equal to 4p, so p is 2. And then our focal width is 8, again, because absolute value of 4p, focal width. So that means that from our focus, we go right, left, 4, so we get a total distance of 8, and there we go. That's personally the method that I will use, but you could instead use the relationship between a parametric equation of a parabola and a rectangular equation of a parabola, or conic equation of a parabola. So if we did it that way, then we know from the equation that our h and our k are going to be 5 and 3. So I know right off the bat that I have 5, 3. And then I know, a pattern or a relationship that I should have pointed out from above is, notice that when we have a horizontal parabola like we have here, our x has the t squared, and when we have a vertical parabola like we have here, our y has the t squared. So it's always that inverse relationship because of how we're solving from one equation to another. So in this equation here, since our y has a t squared, I know that it's going to be an x squared equation. Again, inverse relationship there. So it's going to be a vertical opening up or opening down. So again, if we're using these patterns, using these relationships, then we have our vertex is at 5, 3, and then our coefficient of t squared is always the reciprocal of 4p. So that means that 4p is equal to -8, so our p-value is -2. So we go with our vertex down 2, et cetera, from our information can create our equation. So our next example, I'm going to do that way first. So in our equation here, since we have the t squared with the x, that means that y squared in our equation. So I go ahead and I identify my vertex is going to be at 0, -3, and the coefficient of t squared is the reciprocal of 4p, so 4p is going to be equal to 1/2. So I know my vertex is at 0, -3, because I'm not adding anything here, -3, and 4p is equal to 1/2, which means p is equal to 1/8. So I go ahead and I put that all together, and again, I know that x is squared, so I have x squared, since it's not minus anything. I said that completely opposite, sorry. Y is squared. Since t squared is with x, y is squared in the equation. Okay. Y plus 3 squared equals 1/2 times x, because 4p x. And again, it's just x because our h is 0. So then we go ahead and we graph this. So our vertex is at 0, -3. And this is going to be opening to the right. So we're going to go 1/8 to the right, put our focus, 1/8 to the left, put our directrix, and we'll have a focal width of 1/2. So very poorly graphed because, again, very tiny example, but that's the general gist of graphing. Now, the alternative way, and again, the way that I will always do it, because you don't have to remember all of these things, is just to solve for t, substitute it in. So we have y equals t minus 3, which means t equals y plus 3. So we go ahead and we take that and we substitute that into the other equation. So we get x equals 2 times the quantity y plus 3 squared. And then we solve for the quantity y plus 3 squared. And then we graph. All right, our next examples. Sketch the parabola with the given information without a calculator. Write the, oh, sorry, I totally forgot to check our everything in our calculator. So let me stop the share. Okay, so when we enter this into our equation, again, you want to make sure you go to mode and then you select, instead of function, parametric equation, so that you have your calculator set up to graph a parametric equation. So we're going to go to our y equal and we're going to enter in our parametric equation. So our first parametric equation has x equals t plus 5. So again, when you hit this button here, it automatically does a t. It knows t plus 5. And then our y equals -1/8 t squared plus 3. So -1/8 t squared plus 3. -1/8, I accidentally did 1/2 t squared plus 3. So now we have that in our calculators. And then we hit graph. I am going to do a zoom 6, just a zoom standard, because I have messed around with things quite a bit. And we graph it, and there we go. We end up getting our parabola. Now, I have just half of a parabola here, and that's because of the way that I have t set up. So I'm actually going to go into my window, and I have t going from 0 to 6.28, which means that vertex is when time is 0. So I'm only moving forward with my positive time. So I want to make sure that I am changing this to, I want to make sure that I'm changing this so that we have the positive and negative time. So I'm going to make t minimum be, let's say, -10, and my t max be +10. And then I'm going to have my t step be, I could leave it as 0.13. So now when I go to graph, there we go. We get both sides of that parabola. And in this case, I probably should zoom out just a little bit more so that I can see a little bit more of our parabola. But if we're looking at our trace feature, we can go ahead and we can kind of scroll through just to verify. And my t-step is 0.13, which is why it's going so slow, because it's moving at 0.13 seconds every little click that I'm doing. But we can see up at our, vertex, is it about what our vertex should be, etc. All right, so that is how we have that graphed. All right, due to time, we're going to skip the second one, but Actually, you know what? I want to do the second one just because the second one is showing that, remember before, I could not graph something like number 4 in my calculator because that's not a function. And my calculator, as of now, we only knew how to graph functions. Well, now I can actually graph something that's not a function, like a circle, like a horizontal parabola, like an ellipse, like a hyperbola, because of a parametric equation. So if we want to really quickly do this next example, type in 2t squared for our x and t minus 3 for our y, and a quick graph of that, again, shows that, hey, now we have a nice horizontal parabola. And mine looks like it's going opposite because you're seeing a reflection, but it is, if you turn it around, look at it the right way, the correct way. All right. Okay, now in our example, sketch the parabola with the given information without a calculator. Write the rectangular form of a parabola, write the parametric form of the parabola, use the parametric mode to verify on your calculator. Okay, so we're doing a whole bunch here. So we're given a vertex is at 4, -3, and our focus is at 2, 3. So we graph that, and we have our vertex, which is at 2, -3, and our focus, I'm sorry, which is at 5, -3, and our focus, which is at 2, -3, which means that our p-value is 3. So again, there are 2 ways that you can go about doing this problem. Either way, you need to kind of get your equation in rectangular form first. So from here, I can identify my p-value is -3, which means 4p is -12. So when I put this into rectangular form, I get y plus 3 squared equals -12 times x minus 5. Again, y plus 3 squared, because this is a horizontal parabola opening to the left. So from here, to put it into parametric form, we can do it one of 2 ways. One is, again, if you have all of those relationships memorized, we know that we have our h, which is going to go be the constant for x, our k, which is going to be our constant for y, and then the reciprocal of 4p is going to be our a value. And since y squared is the rectangular, t squared will go with x. So we put that all together and we get x equals -1/2 t squared plus 5, y equals t minus 3. Again, I don't do it this way. I use a substitution. So just like we did in our last example, where we solved for t, substituted that in, we're going to take what's not being squared and make that equal to t. So we're going to start with the x minus 5 and set that equal to t and go from there. So we start with I said that opposite, sorry, with what is being squared and set that equal to t. Let me erase that top part. So we start with y plus 3, set that equal to t. So we have y plus 3 equals t, and truthfully, it doesn't matter which one you do. Both will be correct. It is easier, though, if you set what's being squared equal to t. So y plus 3 equals t, which means y equals t minus 3. And then we substitute that in. If y equals t minus 3, then that means that t squared equals -12 times x minus 5. I just substituted that in here. And then we go ahead and solve for x, because we already have our y equation. Now we need our x equation. So divide by -12, add 5, and there's our other equation. So we get our set of parametric equations. Y equals t minus 3, x equals -112 t squared plus 5. All right, so our second equation here, our focus is at -4, -1, and our directrix is the line y equals -6, which means our vertex is going to fall right in the middle there at -1, 2, 1, 2, 3 and a half. So x equals -1, 2, 3, 4, -3.5. So there's our vertex. And we know that the number that or the direction it's going is opening up. So our p-value ends up being 5/2, or 2.5 if you're counting vertex up, vertex down. So we go ahead and we put this into our rectangular form, and we know that x is going to be squared because it's opening up, +4 p-value because it's opening up. So we end up getting x plus 4 squared equals 10 times the quantity y plus 3.5, because again, our vertex was at -4, -3.5. And again, I got -3.5 because it's exactly in between -1 and -6. All right, so I'm gonna go with the substitution method first. So in this equation, since x plus 4 is being squared, I set x plus 4 equal to t and solve for x. So I get t equals x plus 4, which means x equals t minus 4. So that is our x equation. And then we take that and we substitute it in here. So we end up getting t squared equals 10 times the quantity y plus 3.5, divide by 10, we get 1/10 t squared equals y plus 3.5, subtract 3.5, and we get y equals 1/10 t squared minus 3.5. So there's our x equation, there's our y equation, we put it all together, and there's our parametric equation. Alternatively, if again we're doing it with patterns, then we would have, since our parabola is opening up, I know for my rectangular x is squared. So since x is squared, the t squared goes with y. Since our 4 p-value is 10, our a value is 1/10, the reciprocal. And then since our x coordinate of our vertex -4, we get x equals t minus 4. And since our y coordinate of our vertex is -3.5, we get y equals 1/10 t squared minus 3.5. Again, either way you do it, whether you use the substitution or you use the pattern. All right, an application problem. So vectors, it seems so long ago that we did vectors, but it actually wasn't that long ago at all. But recall from the chapter on vectors that if a ball is thrown at an initial velocity of 50 feet per second at an angle of 30 degrees, find the vertical and horizontal components of the velocity. So we go ahead and we draw 50 feet per second. We want to know the horizontal and the vertical. So we end up getting cosine 30 equals x over 50. So x equals 50 cosine 30. And then we have sine 30 equals y over 50. So y equals 50 sine 30. So we end up getting the vector 50 cosine 30, 50 sine 30. Or if you remember that we can end up getting the vector as magnitude times cosine theta, magnitude sine theta. So in this case, velocity cosine theta, velocity sine theta. But there are more things that affect the ball other than velocity, initial velocity. For example, gravity. So recall from math 2, it's been a while, we have an equation to represent a parabola that's being affected by velocity or gravity over time, so projectile over time. And we have h of t, which is height at time t, equals -16 t squared plus v initial times t plus h initial, which is our initial height. So v initial, initial velocity, h initial, initial height. And yes, this just needs to be memorized. So what we're going to do now is we're going to take a parametric equation and we're going to separate what's happening to this ball over time. So in this case, this equation here represents height over time. So that is strictly just the vertical component. And then here, if we want to know horizontal distance over time, well, that's what we were doing over here. So to take a parametric equation which separates the two, how does horizontal change over time versus how does vertical change over time, we get the two sets of parametric equations. So x is going to be v initial cosine theta times t, because again, change horizontally over time. And our height equation, our y equation, is going to be negative 16t squared plus v initial sine theta times t plus h initial. So when you have this set of parametric equations, you're actually able to look at both the distance horizontally over time as well as the height vertically over time, both in one equation, instead of before where we had to separate the two when we're talking about rectangular. So these two together end up being our set of parametric equations for projectile motion. Again, just memorize. So let's go ahead and let's do an example. A player hits a baseball at 3.2 feet above the ground with an initial velocity of 142 feet per second at an angle of 21 degrees. With the horizontal, write a set of parametric equations that models the situation. Use the trace feature on your graphing calculator to find maximum height of the ball, the distance the ball traveled before it hit the ground, and how long the ball is in the air before it hits the ground. So let's go ahead and let's start by coming up with our set of parametric equations. So I like to draw a little sketch to kind of help me remember everything. So we have initial velocity, angle, initial height. So we get x is 142 cosine 21 times t. Notice our angles in degrees, so we want to make sure our calculator is in degrees before we do this example. Y equals negative 16t squared plus 142 sine 21t plus 3.2. All right, so let's go ahead and let's type this in. So again, we're going to want to go to mode and make sure that we are in degrees, which I was not in degrees. And now we're going to go to our y equals. So for our x, we have 142 cosine of 21 t. And it is really important that you do not have 142 cosine of 21t. It's just cosine of 21 and then times t. So that whole thing, 142 cosine 21, is your coefficient of t. So make sure t is not included in the, you're not taking the cosine of it, all right? And then y equals negative 16t squared plus 142 sine of 21 t plus 3.2. All right, I'm going to graph this, but I'm going to change my window quite a bit because we're going to, I just had a zoom standard, so it was negative 10 to 10. So we're going to assume that this ball is going to go higher than 10 feet and farther than 10 feet. So maybe do a quick zoom fit. Let's see how zoom fit did. My calculator's freaking out. Maybe I shouldn't have done a zoom fit. There it goes. Not bad. All right, so I get a graph that looks somewhat like that, but I can't, I'm gonna have to change that. So go to my window see, X minimum, I'm gonna make be -10. My X minimum, let's go ahead and say like 200. X scale, go by 5s. Y minimum, -10. Y minimum, we'll say 200 and go by 5s. Okay, now I'm gonna graph that.